All right, so this final video is going to be looking at non-spontaneous electrochemical cells and the process where we are able to produce an electrochemical reaction that is non-spontaneous is called electrolysis. It's when we force a current through a cell that's going to generate a negative cell potential and use that electrical energy that we've been talking about harnessing from our galvanic cells to produce a chemical reaction. So here's an example of the galvanic cell on the left, where zinc is transforming copper ions into copper metal um, when we reverse it. And now we have the copper converting the zinc ions into zinc metal. The cell potentials are identical, except that one is positive on the galvanic side, and the other one is negative on the electrolytic side. You will notice that the components that are making up your anode and cathode have reversed because now zinc is being oxidized in the galvanic side while copper is being oxidized in the electrolytic cell. So the oxidation reactions still occur where they were before, and the cathode reactions are still going to be the site of reduction. But the electrons are still going to be moving from anion to cation, from anode to cathode, but you have to have some sort of energy source in the electrolytic cell to push those electrons to be able to overcome that voltage, the negative voltage that's present between those two half reactions. So the power source allows those electrons to continue to move from anode to cathode, but to move in the reverse direction than what you would normally expect. So this reaction will not occur spontaneously. You need to have more of a potential than what your cell actually needs, since you're going to lose some of that energy, kind of like what we talked about with thermodynamics, through heat changes and things like that. Electrons again flow from anode to cathode, and I said typically again that your cathode tends to be found in the left compartment in an electrolytic cell, and the anode and the right compartment, since they've switched this. Yay, fun. But again, please remember that you're looking for the oxidation half reaction for the anode and for the reduction half reaction for the cathode. The ions still need to flow to balance out the charges. Cations are still going to flow towards your cathode, and anions are still going to flow through your anode, towards your anode through that salt bridge. So if all we are electrolyzing is a salt, then both the anion and cation are going to undergo the half reactions. The anode is going to be where your anion is oxidized, and your cathode is where your cation is going to be reduced. So here we have molten lithium iodide. And so if we wanted to write the half reactions for both of these, again, I believe they're both on your chart, so you can use that as a reference, or you can write them like we did previously. We want to turn lithium into lithium ions, we want to turn lithium ions into lithium, okay? Because the salt would be charged particles, the cation and anion. And so we see that if for lithium to be reduced, it's got to gain an electron. While for iodide to be oxidized, it's going to go from -1 to 0. And so we would need two iodines to balance out that iodide molecule that is formed. Okay? Because two iodides needed to produce one iodine molecule, two electrons would have to be lost to allow that to take place. So there's our two sets of electrons. We see that although these two are now balanced by atoms and by charge, we don't have the same number of electrons being lost by the iodine ions as we do being gained by the lithium ion. So we need to double the reaction on top. When we combine those together now, we would get our complete net ionic equation showing the electrolysis of lithium iodide into its pure metal form lithium and into its pure non-metal form iodine. More often, you're going to run into salts that are in solution with water. And water is able to go through both oxidation and reduction. So we have to look at both components. We have to look at the anion that's present in our salt, and we have to look at water. And we have to compare their voltages. And the best way I can tell you to think about this, it's the easiest way out. Which one of the two half reactions where oxidation is occurring is going to require less energy to be able to allow that half reaction to proceed? That's the half reaction that's going to take place. Why would you use up more energy if you can use less and get that half reaction to occur? It's going to be the same thing with the cathode. So just like we saw before in the anode, we're looking to see is the anion being oxidized, or in this case, is water being oxidized, since we have two possibilities. And when water is oxidized, it's going to produce oxygen as well as hydrogen ions. At the cathode, we're either going to see that cation reduced to its pure form, or we're going to see water reduced to hydrogen and hydroxide ions. To do this, we're going to have to look at our chart. Again, the two water half reactions are on your chart. So we're still dealing with that half reaction for lithium. And if we look at that lithium's half reaction on your chart, you're going to see it has a very negative cell potential, negative 3.045 volts. When I look at water's half reaction for being reduced, I see that it has a smaller negative cell potential, negative 0.8277. So it's going to require less voltage to allow water to be reduced than it is going to be to reduce lithium ions. When I look at my anode half reactions, I'm going to be looking to see, is iodide going to be capable of being oxidized? So to be oxidized, I would need to flip that reaction on your chart, and it has a negative cell potential of 0.4535 volts. And then I'm going to take the half reaction for water undergoing oxidation and flip it, and I see that it has a much more negative cell potential, negative 1.229 volts. Again, I want to use the half reaction that's going to require less voltage, less energy to allow this reaction to proceed. So on the cathode side, I would want to use the water half reaction with the smaller cell potential. And on the anode side, I would want to use the iodide half reaction. When I combine those two together, they're going to require a little over 1 volt of energy. If I had combined the lithium with the iodide, it would have been over 3.5 volts of energy would have been needed. And so hopefully you can kind of see with that analogy, the smaller amount of voltage is going to get this reaction to proceed, rather than in adding a greater amount of voltage. It's not that you couldn't get the other one to go, but if you can get one to happen without requiring as much energy, it's going to go in that direction. Now that I have both my anode and my cathode half reactions, if I look at them, I see that they have the same number of electrons being transferred, so I don't need to account for that when I combine these two together to write my balanced net ionic reaction. I take the two half reactions, I cancel out my electrons, I combine my reactants, I combine my products, and that would give me the balanced equation for lithium iodide undergoing electrolysis when it is in solution, when it's dissolved in water. The last thing we're going to talk about with electrolysis is how we can use um, the current that we have present and the chemical reaction, how we can relate electricity to mass quantities, how we can figure out how much of a particular element is going to be generated, or how we can figure out how long we're going to need to allow the electrolysis to proceed to produce so much of a material. And so we know that current is going to be in amperes, which is a form of coulombs over seconds. And we've talked about Faraday's constant before, about how that relates coulombs to moles of electrons, our charge to our time and our charge to our moles of electrons. The moles of electrons is the kind of the transition between the two, because the moles of electrons relates to the electrical component, and it relates to the mass component in terms of how much of your chemical substance, your analyte, you have present. So that's going to be our transition between electrical land and mass land. In this particular reaction, the electrolysis of BiO plus produces pure bismuth. I've got that half reaction written for you there. I had to use water to balance out the oxygens. I had to use hydrogen ions to balance out the hydrogen atoms in water. And when I go through and look at my electrons, I have a positive 3 charge on the reactant side. I was neutral on the product side, so the half reaction, the electrons were gained on the reactant side, and I had to have 3 of them. I want to know how long it would take to make 10 grams of bismuth by electrolyzing this solution with a current of 25 amperes. So I want to know about the time. I know how much of the bismuth I have, and I know the current for that I'm allowing the electrolysis to take place with. So since I want to know about time, I'm wanting to know about the electrical side of things. So I need to start on the opposite side. I need to start on the mass mole side. So if I take my 10 grams of bismuth, I can convert that to moles with its molar mass. Sorry. I look at my balanced equation, I can relate bismuth to the moles of electrons, that for every 1 mole of bismuth, I'm going to gain 3 electrons. We know that for every electron that is transferred, we are going to need to have 96,485 coulombs of charge. And we talked about how amperes can relate to seconds by saying that 1 ampere is the equivalent of a coulomb per second. So using that current, I can get back into time. My gram units are going to cancel, my moles are going to cancel, my moles of electrons are going to cancel, and my coulombs are going to cancel. The Coulomb constant will not affect your sig figs. The moles of electrons are an exact value. So if we look at our sig figs, we have 3 in the bismuth, 5 in the molar mass, and 3 in our current. So we want 3 sig figs in our answer for time. And it would take 554 seconds if we solve this mathematically to generate 10 grams of bismuth via an electrolysis of this solution with a current of 25 amperes. So this time we were looking at it more on the electrical side. In our final example, we're going to look at it on the mass side. I want to know how much chromium can be made over a period of 1 hour if I electrolyze a potassium dichromate solution with a current of 15 amperes. The dichromate is what's going to be going through electrolysis. You've got the half reaction there. This one is on your chart. If you want to go over how to balance it and you're not sure, let me know. Because I'm wanting to find the chemical side, the mass side, I'm going to use the electrical components to help me get there. I'm going to go from the opposite direction. And then we talked about how time and current can help us to get coulombs. We know that coulombs can help us to get moles of electrons, and from there we should be able to get to mass. 1 hour is the equivalent of 3,600 seconds. 60 minutes in an hour times 60 seconds in a minute. I need to get to seconds because amperes are the equivalent of a coulomb per second. Now that I'm in coulombs, I can relate that to moles of electrons with Faraday's constant. If I look at my balanced equation, I'm wanting to produce chromium, and I see that 2 chromiums were needed or 12 electrons were needed to be gained to form 2 chromiums. Make sure that the ratio is what it is for that metal and the moles of electrons in your balanced half reaction. And if I want to find the mass of chromium, I'm going to need its molar mass from the periodic table, 52 grams per mole. My hours cancel, my seconds cancel, my coulombs cancel, my moles of electrons cancel, and my moles of chromium cancel. In terms of sig figs, I had 3 sig figs in my time, 3 sig figs in my current. Faraday's constant had well more than that. We don't worry about the relationship from hours to seconds. We don't worry about the relationship from our balanced equation with the coefficients. Our molar mass had 4 sig figs, so we want 3 sig figs in our answer, and I got that would give you a mass of 4.85 grams.